Hi, everyone, and welcome back to Psych 3530. You should have just finished up reviewing a lecture on independent groups or between groups research method designs. And so, what we're going to do in this lecture is break down and use the statistical test that goes along with a between subjects research design. Because remember, the decisions we make on the methodological design side have direct one-to-one correspondence and impact on the statistics that we must use on the back end once we have the data. So the decisions you make, like, do I collect data from 2 groups of people or 3 groups of people or 4 groups of people? Do I follow people over time? Those sorts of methodological decisions directly impact the statistics that we have to use. So, in the case of an independent groups design or a between subjects design with 2 and only 2 groups of people, we need to use what's called an independent samples t-test. This is what an independent samples t-test looks like. We're going to break down this formula a little bit and then use it in an example. So, first things first, let's break down the numerator versus the denominator. The numerator is easy. It's the mean difference between our 2 groups. So let's say we're studying levels of depression in 9th graders versus 12th graders. Well, we would find the mean level of depression in 9th graders, group 1, and subtract it from the mean level of depression in 12th graders, group 2. Right? How different are 9th graders and 12th graders in their average levels of depression? Easy peasy. Numerator is straightforward. The denominator requires a little more arithmetic, although I want you to notice that there's nothing crazy here. This is nothing beyond basic middle school algebra, right? If you can add, subtract, multiply, divide, do an exponent and take a square root, and then do it in order of operations, then you can do this statistic by hand. Arithmetically, it is not complicated. What's more difficult to understand is sort of why the statistic is set up this way and what it tells us. And so that's what we're going to really spend most of our time on. Right? The math is straightforward. The what and why is what takes a little bit more time to understand. So if the numerator is just the difference between our groups, the denominator ends up becoming something like the amount of variability that we would expect between our groups just due to chance. I'll say that again. The amount of variability we would expect between our groups just due to chance. So, when we collect data in an experiment, we have to sample from the world. That sampling procedure means that we're not looking at everyone in a population. We're looking at a subset of people, and the particular subset from which we collect data is going to vary randomly in ways that we can't necessarily control. We can try to control it as best we can, but we're never going to be able to completely control it. If I'm looking at 9th graders, I have to collect a random sample of 50 9th graders. That random sample of 50 9th graders is going to be a little different from any other random sample of 50 9th graders. There's uncontrollable variability there. And so we can estimate the amount that we would expect 9th graders and 12th graders to differ just because of random chance. That's kind of what the denominator is the expected amount of variability. So if our numerator is the actual amount of difference between our groups, and the denominator is the expected random amount of difference between our groups, then what we have with our t-test that will produce a t-value is a ratio of actual difference divided by expected difference. actual difference divided by expected difference. And because this is basically a fancy fraction, right, numerator and denominator, the resulting value, our t-value, the larger our t-value, the larger the difference between our groups, and the more that difference exceeds our expectations. The smaller the t-value, the smaller the difference between our groups, and the more sort of normal that difference looks, such that a large t-value leads us to conclude that the groups differ, and a small t-value leads us to conclude that the groups do not differ. So if we get a big t-value, it's more likely that we're going to claim that 9th graders differ from 12th graders. Let's break this down with our numerator and denominator. Remember, it's a fraction. So if the numerator is big, then the resulting number is more likely to be big, right? So if our 9th graders and our 12th graders are very different, then this difference is large, which is going to produce a large t-value. Now, if our denominator is small, meaning that there's a small amount of expected variability between the groups, if our denominator is small, then the t-value also gets bigger, right? 10 over 1 is 10. 10 over 10 is 1. 10 over 100 is 0.1, right? So the bigger the numerator, the bigger the t-value. The smaller the denominator, the bigger the t-value. So sort of the perfect storm of a significant difference between two groups is a large mean difference and a small expected difference. And let's think about what that means. If we expect the groups to be very similar, right, to have small amounts of variability, but then it turns out that the groups are actually very different from one another, what that means is something significant is going on. Right? We expected 9th and 12th graders to be the same. Then it turns out 9th and 12th graders are very different. Therefore, we get a big t-value. Therefore, we should conclude something is making these 9th graders different from these 12th graders, right? Something significant is going on because our observation of the world, the numerator, outpaced our expectation of the world, the denominator. Remember, we use this test, this formula, when we collect data from 2 independent samples of people. They'll produce 2 group means, and we don't have population level data. So if I'm interested in 9th and 12th graders, I can't possibly collect data from every 9th grader and every 12th grader in the country. That's impossible. Right? That would be the population. I don't have access to the population. I have access to a sample, a subset of 9th graders and a subset of 12th graders. So I do the next best thing. I measure that subset, right? 50 9th graders and 50 12th graders. And then what I'm going to do is I'm going to make an inference from my sample to the population, hopefully that allows me to use my samples to learn something about all 9th graders and all 12th graders. So let's set up an example that we're going to use throughout the rest of this lecture. Let's imagine that maybe we're studying mental health counseling in trauma victims. And we want to know, is expressive writing a form of sort of mental health activity or counseling that actually impacts people's overall health, maybe their physical health even? So does engaging in expressive therapeutic writing impact the overall health of trauma victims differently from trauma victims that do not engage in expressive writing? So what we're doing is we're setting up two independent groups. We're going to have, let's say we get 20 people. We randomly assign 10 of them to engage in expressive writing. And then we randomly assign 10 of them to do nothing, right? To not expressively write. And then we're going to wait a little while, and then we're going to measure their health. At this point, it's not really important how we measure their health. Let's just say we give them a survey with a bunch of questions, and then it collapses into a single measurement, a single number that quantifies their health. And we want to see, does expressive writing impact health versus people who do not engage in expressive writing? So our independent variable, the thing that we manipulate, is expressive writing. Our dependent variable, the thing that we measure, is health. Now we can set up this scenario with our research question and our hypotheses. First, our research question is, does expressive writing about trauma affect one's physical health? Notice the non-directional language. Notice the ambiguity of the word affect. Affect could mean increase health. Affect could mean decrease health. So what we have here is a two-tailed or a non-directional hypothesis. Thus, our null hypothesis can be expressed as group 1 will be equal to group 2, right? That's the nothing happened hypothesis. Nothing's going on. Expressive writing doesn't do shit, right? Doesn't help anyone, doesn't hurt anyone. Group 1 is equal to group 2 after they expressively write. And remember, this hypothesis is, as scientists, where we start, right? We start with the idea that nothing is happening. But we can set up this alternative or research hypothesis, which is that something happened. Right? We engaged in expressive writing, and now group 1 is not equal to group 2. We don't know, we're not sure if they're going to be lower, we're not sure if they're going to be higher, but maybe they end up being not equal. So we're going to start with the null, and we hold on to the null, and we only move to support the alternative if the data suggests that we should. And the thing that tells us whether we should move from the null to the alternative is our t-test. That's the tool that we have to tell us, do we stay with the null, in which case we had a small t-value, or do we move to support the alternative, in which case we had a large t-value? Again, we want to be clear that our populations here, right? Maybe population 1 is students who engage in expressive writing. Population 2 is students who do not engage in expressive writing. Let's break down the formula. The numerator's easy, right? We went out into the world. We collected data on expressive writers and non-expressive writers. The numerator is the average health score of expressive writers minus the average health score of non-expressive writers. Easy peasy. The denominator takes a little bit more work. So let's break down what this formula means, and then we'll go look at the calculations. So the first thing we have to do is find our sample variances. That's what S1 and S2 are. S1 is the sample variance of group 1. S2 is the sample variance of group 2. We're going to do that using a sum of squares table, which you should remember from 3510. Then, once we find our sample variances, we're going to use those sample variances along with n, which is the number of subjects in group 1 and the number of subjects in group 2, to calculate our denominator, basically the expected amount of variability in our samples. Again, don't let this confuse you. Don't let it intimidate you. The algebra is middle school level algebra. Can you add? Can you subtract? Can you multiply? Can you divide? Can you do an exponent? Can you do a square root? And can you do it all in order of operations? Nothing crazy here. Nothing to get freaked out about. So let's start with the math. Let's find our sample variances. Let's imagine that we collected our data. We have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 each of expressive writers, and then our control group are non-expressive writers. Each of these numbers represents an individual that's within each group, and these numbers are our outcome, our dependent variable, health score. So we list all of our expressive writers, and we find that their average, their mean, is 79. We list all of our control group, our non-expressive writers, and we find that their mean is 68, right? Add them up, divide by 10. Our next steps, and I've just gone ahead and done the math out so that we can take a look at it. Our next steps are to do a sum of squares table for each group. One for expressive writers, one for the control group. So remember, in a sum of squares table, we find the mean, and then we take each value, each x, and we subtract it from its own group mean. So 77 minus 79 is negative 2. 88 minus 79 is 9. 77 again minus 79 is negative 2. 90 minus 79 is 11. So on and so forth. Notice that when a value is equal to the mean, right, it produces a score of 0. We take these difference scores or deviations, and then we square them to get a squared deviation. So negative 2 times negative 2 is 4. 9 times 9 is 81. Negative 17 times negative 17 is 289. So on and so forth. We get our squared deviations for each participant, and then we add them up. We sum the squares, right? SS, sum of squares. We have summed the squared deviations. For our expressive group, it equals 850. We do the same thing, just using its own values and mean over here for our non-expressive, our control group. And we get a sum of squares of 1002. And so now we can move forward to calculate our variances. So we take each n, which is the number of people in group 1 and the number of people in group 2. We find degrees of freedom for each group, which is n minus 1, which is 9. We already have the mean for each group. We already have the sum of squares for each group. We need a sample variance for each of our groups, S squared. So sample variance is the sum of squares divided by degrees of freedom. 850 divided by 9 is 94.44. 1002 divided by 9 is 111.33. So remember, degrees of freedom is n minus 1, right? 10 people minus 1 equals 9. 10 people minus 1 equals 9. We take sum of squares, which we found here. We divide each sum of squares by its own degrees of freedom to produce our sample variances, our S squares. So now we just need to plug those S squares into the formula, right? Look, I have S1 squared and S2 squared. I've already got each of these values. S1 squared was 94.44, S1 squared. S2 squared was 111.33. So what I'm going to do is just plop those numbers into each of these values, then plop their sample size into each of these. So that'll be 10 and 10. And then we just do the algebra. So let's break that down. S1 squared was 94.44 divided by 10, which was N1, plus 111.33, which was S2 squared, divided by 10. 94.44 divided by 10 is 9.44. 111.33 divided by 10 is 11.13. We add those together to get 20.57. So that's the result of everything under the square root, right? We took each s squared and divided it by its n, and then we added them together to get 20.57. Then we have to do the square root. Square root of 20.57 gives us a denominator of 4.54. This 4.54 represents the amount of difference in health that we should expect between our expressive group and our non-expressive group, basically just by chance, just kind of randomly. Randomly, there's going to be about this amount of difference in health between expressive and non-expressive writers. So now that we know our denominator is 4.54, we can just replace all of this algebra with the number 4.54. We already found the mean of expressive writers and the mean of non-expressive writers. It was 79 and 68. That's way back here. Remember, we found the mean of the expressive writers and the mean of the non-expressive writers. So we pull all of those numbers together. 79 minus 68, the mean difference, divided by this denominator that we just calculated to be 4.54, gives us a t-value of 2.42. That's what we're after. That t-value is going to tell us, do expressive writers differ enough from non-expressive writers such that we should conclude that expressive writing matters, that expressive writing changes something. This value, this t-value, is our key to unlocking that answer. But remember, we're doing hypothesis testing, so we need some benchmark. We need something to compare it to. For that, we need our t-distribution critical value table. We use 3 pieces of information, as we discussed in our review of hypothesis testing. We need the total degrees of freedom, which is just the degrees of freedom of group 1 plus the degrees of freedom of group 2. Remember, degrees of freedom is n minus 1 for each group. I had 10 expressive writers. That gives me 9 degrees of freedom. I had 10 non-expressive writers. That gives me 9 more degrees of freedom. 9 plus 9 is 18. Let's say alpha is 0.05. I don't think we defined that yet, but let's just define it now as 0.05. And remember, we had a two-tailed hypothesis because we made a non-directional hypothesis. So we use these three pieces of information to find our critical t-value. So first, we're working on the two-tailed row here. We're not one-tailed, we're two-tailed. We're going to come over here and we're going to find our alpha, which is 0.05. And then we're going to find our degrees of freedom, which is 18. We're going to triangulate that column and that row to produce a critical t-value of 2.101. Again, two-tailed test. Alpha equals 0.05, so we know we're using this column. And we've got degrees of freedom of 18, so we know we're using this row. And we just find where that row and that column meet, 2.101. So Our critical t-values, our benchmarks, our lines in the sand, are plus or minus 2.101. Why plus or minus? Because we have a two-tailed hypothesis. So we want to set up our hypothesis testing like this. We have this distribution. At the 0 point, what that means, if we were right here, it would mean that our expressive writers are exactly equal to our non-expressive writers. As we move to the right, our expressive writers have better health than our non-expressive writers, right? Because that would produce a positive t-value. As we move to the left, our expressive writers would have worse health than our non-expressive writers, because that would produce a negative t-value. We have a two-tailed hypothesis, so we take our 2.101 and we use it as a benchmark on either side of the curve. Because remember, we weren't sure if expressive writing was going to make health better or was going to make health worse. So we're giving ourselves a chance on either side of the curve. These are our benchmarks. We then add to that our experimental t-value, the observed t-value. How different were our groups? Well, they were 2.42 different. That's right here, the red line. Our red line is more extreme than our benchmark, right? We have exceeded the critical value, which means that the groups significantly differ. The difference between expressive writers and non-expressive writers is so extreme, right? It's way out here in this extreme uncommon area of the curve. It's so extreme that we are convinced. The extreme difference between writers and non-writers convinces us that writing does something. Right? Writing increases health because we're on the right side, the right-hand side of the curve here. Expressive writing looks like it increases health significantly. So we are more extreme than the cutoff. Therefore, we reject the null. And this is where the logic can get a little confusing. Remember, the null is the idea that the groups are equal, right? That's where we start. We start with the idea that they are equal. But we just found that they are not equal, right? They are extremely different from one another. So what we do is we reject the idea that they are equal. We reject the null, and we conclude that expressive writing does, in fact, increase people's health after trauma. Now, the next thing we need to do, because we have a significant effect, is we need to calculate an effect size. We do this with Cohens D. Cohens D is the way of quantifying the difference between two groups. And we're going to have a benchmark for interpreting this Cohens D. A Cohens D of 0.2 is considered a small effect. 0.5 is a medium or moderate effect. 0.8 is a large effect. Here's the formula for Cohens D. It's, again, our mean difference, right? Doesn't, group A minus group B, right? Expressive writers minus non-expressive writers. Ignore the fact that this is now 2 and 1 and 1 and 2. It doesn't matter as long as you stay consistent. Divided by, this looks similar. It's not quite similar. It's not quite the same, but it looks similar to our t-test denominator. It's the squared standard deviation, which is variance, which is the thing we already found, right? The squared standard deviation of each group added together divided by 2. So basically, variance plus variance divided by 2, take the square root. So we'll do it again, right? The numerator is 79 minus 68, our mean difference. The denominator is the square root of the variance of group 1 plus the variance of group 2 divided by 2. So 94.44 plus 111.33 divided by 2 is 102.89. The square root of 102.89 is 10.14. We take 10.14, that's our denominator. So we say our mean difference, 79 minus 68, divided by 10.14 equals a Cohens D of 1.08. This is a large effect. We'll go over the math one more time. Take each variance, right? The squared standard deviation is variance. So the variance of group 1 plus the variance of group 2 divided by 2 equals 102.89. The square root, right, that's this guy. The square root of that operation of 102.89 is 10.14. 10.14 becomes our whole denominator. And we're going to divide our numerator, which is our mean difference, 79 minus 68, divided by our denominator, gives me a Cohens D of 1.08. So now, we need to write up an APA-style conclusion that communicates these results to a reader. This is important. I don't want to say the most important, but the ability to write up an APA-style conclusion is critically important because the point of doing science is to communicate to other people, right? If we don't communicate to other people, who cares? What does it matter, right? The point of science is to communicate that to other people so that they can understand it and better their lives. But if we can't communicate effectively, then our science is worth nothing. So we need to have this systematic, clear way of communicating our results, and that's known as an APA-style write-up. There's a few parts to it. The first sentence should be, what test did you run and what was the research question? An independent samples t-test was conducted to examine whether expressive writing about trauma affects one's health. What test did you run and what was the research question? The next sentence is a summary of our statistical findings. We give the we give the descriptive statistics for each of our groups. The expressive writing group's rating of their physical health, mean of 79 with its standard deviation. That's just the variance. The square root of the variance. The average person who engaged in expressive writing had a mean health rating of 79 with a standard deviation of 9.22. Was significantly greater than the control group's physical health rating and standard deviation. This is the part that we have to be really careful about. There is no ambiguity in what I call the T statement. T, that tells us we did a t-test. Parentheses 18, that's where we put our total degrees of freedom. So our 9 degrees of freedom from group 1 plus our 9 degrees of freedom from group 2 equals 2.42. That was the result of our t-value. P is less than 0.05 because we had a significant difference with an alpha of 0.05. And our Cohens D was 1.08 with a two-tailed test. So that's our summary of statistical findings. We give both the descriptive statistics and what we call the inferential statistics, the T stats. So we have the mean of each group again, the standard deviation of each group, our degrees of freedom total, our calculated t-value. P was less than alpha because we were significant. Cohens D was 1.08. And we had a non-directional or a two-tailed hypothesis. The last piece of our APA style write-up is our take-home message, our conclusion. This should be something that a fourth grader can understand, right? Break down what has happened and communicate it in such a way that any reasonable person can understand it. It doesn't have to be complicated. It can be quite simple and short, as this one is, right? So an independent samples t-test was conducted to examine whether expressive writing about trauma affects one's health. The expressive writing group had these physical health ratings. They were significantly greater than the control group's physical health ratings. T 18, 2.42, P is less than 0.05, D equals 1.8, two-tailed. The point of the conclusion is that someone who is unable to understand anything else in the APA style conclusion, because this is a lot of information and it's a lot of very technical and specific information, provide a conclusion such that someone who doesn't even understand these first two sentences can understand the take-home message, which is, thus, expressive writing increases physical health. Boom. That's it. It doesn't have to be more complicated than that. Express the important idea in a way that is communicable to the average person. Explain it to a fourth grader. That's what I always try to do when I write AP style conclusions. Now, what would happen if it was not significant? The first sentence stays the same. The first sentence stays the same because nothing changed. The second sentence mostly stays the same. We still provide our descriptive statistics for each of our groups. But now, instead of saying that they were significantly different, we say they were not significantly different. We would have our T statement, but we would change P is less than 0.05 to NS because we were not significant. We were not less than alpha of 0.05. Thus, expressive writing does not change ratings of health. And our conclusion would, of course, change given that we were not significant. Okay. So if you understand how to do that from the point of getting data all the way through the calculations, all the way through the APA style conclusion, then you can do perfectly well in this class. What I'm going to do now for the next 10 slides is explain a little bit of the theory behind what we just did. You should know this because this theory helps us understand why we use particular statistics, and that's always really important. But think of this as separate from the math, right? You can learn how to do the math and learn how to make the decisions, but then we also need to know why we're doing what we're doing. So that's what this is about, the theory behind all of that. So first, really the denominator is the only thing that matters, right? The numerator is the mean differences. So we're going to focus on the denominator here of our t-value. So we found our sample variances. Variance is a measurement of variability, how much variability there is within each of our groups around its mean. When we have a population variance, we take the sum of squares divided by n. But we don't have data on the population. We have data on a sample. So to calculate a sample variance, we say sum of squares divided by n minus 1, which is degrees of freedom. The sample variance takes into account the error that will undoubtedly occur because we're using a sample instead of using the population. So basically, by using n minus 1 instead of n for our sample variance, we artificially inflate the variance to account for the fact that we're working with a sample and we're not working with the overall population. Now, why would we do that? Because we know that if you pull from just a sample, you're unlikely to capture the extremes of a variable. For example, let's think about the height of the average Georgia State student. The height of the average Georgia State student. Let's just throw males and females all together. It doesn't matter. One big group. And so the average height is probably something around like 5'6", 5'7", right? If you combine males and females. If we were to sample 10 random Georgia State students, I would gather that we would have people around that, 5'5" to 6 foot, 6'1" range, right? If we only sampled 10 people, we're unlikely to get anyone who's really extreme on height, because there are people who go to Georgia State that are 6'10". Right? They exist. They are the extreme level of the population on the high end. Those people who are 6'10", they go to Georgia State. I'm sure there's a few of them out there. But if we were to only sample 10 random students, it's unlikely that we capture someone who's 6'10". It's incredibly unlikely, because out of the 55, 60,000 Georgia State students, maybe there's 5 or 10 of them that are that tall. Maybe. We're not going to capture them in a sample of 10 random students. So if we're not capturing the extremes, then what that means is a sample always underestimates the variability of a population. It always does, because the sample is more likely to gather people who are close to the mean and not people who are extremely short or extremely tall. To compensate for that, when we have a sample, we divide by n-1 to account for that underestimation of sampling variability. Next, finding that denominator using these sample variances. So let's think about this population as the population of people who engage in expressive writing. This population as people who do not engage in expressive writing. And remember, we're measuring their health, right? That's what each of these distributions is, their health. Because samples always underestimate variability, when we sample groups of people, they will look like this. They'll have a tighter distribution because the average sample will be close to the average of the population, and it's very unlikely to get a sample out here in the tails. So sampling always reduces variability. Let's think about it this way. Let's use Georgia State students again. Let's say that we know that the average Georgia State student is 22 years old. I have no idea if that's true. Let's just say it is. I could sample one group of 50 students, and it would be very reasonable that I come up with an average of 20 and a half years. If I sampled again another 50 students, it would be very reasonable for me to have an average of 24 years. If I did it again, it'd be very reasonable for me to be right at the mean, 22 years. If I did it again, it'd be very reasonable for me to be at 22.7 years. Notice how these are all really close to each other and all really close to the population average. Because when I average 50 people's ages, it's going to approximate the population average. What would be really, really weird is if I collected data from 50 Georgia State students and their average age was 40 years old. That would be ridiculous, right? 50 students who averaged 40 years old when we know that the average age of the population is only 22. So when we sample, we reduce variability. We call this the distribution of means, the DOM. The distribution of sampling means always has reduced variability over the population, because it would be crazy to randomly sample 50 Georgia State students and for their average to be 40 years old. But it would not be weird at all to choose a single student and have them be 40 years old, right? I mean, that would not surprise anyone, because A single student is functioning at the level of the population, right? They're one person within a population. That one student could be anything. I mean, I think I just read a story about some like 15-year-old kid that graduated from one of the perimeter campuses, right? You could choose one random student and it could be anywhere from 15 to 80 because it's just one person. So there's lots of variability at that level of the population. But as soon as I start sampling and as soon as I start averaging, for example, 50 students together, then their average is going to coalesce to the population average. It would be weird and very unlikely if it didn't. So when we sample and we create these sample means, their distributions fall along reduced variability. The next thing we have to consider is that when we're doing a t-test, we're not talking about a sample. We're talking about one sample being compared to another sample. This is called the distribution of differences between the means. So the difference between sample 1 and sample 2. And here's where we really get our denominator of the t-test. Is if we take an infinite number of random samples from group 1 and we compare them to an infinite number of samples from group 2, what should we expect to happen? Well, if the groups are equal, right, our null hypothesis, which is where we start, if the expressive writers are in fact equal to the non-expressive writers, then any given sample from expressive writers should basically not be different from any given sample of non-expressive writers. Right? The average difference between those two samples should be 0 because the populations are the same. That's right. That's what the null hypothesis claims. I'll say that again. A random or the average sample of writers should be equal to the average or a random sample of non-writers. The differences between a mean of writers and a mean of non-writers should be 0 if writing doesn't matter. And remember, that's where we start. We start with writing doesn't matter. So we start with the assumption that the differences between our means are 0. But it doesn't always work out that way because of random sampling variability. Remember, sometimes I'm going to get an age that's a little lower than the mean. Sometimes I'm going to get a result that's a little higher than the mean. Sometimes I'm going to get a result that's right on the mean just because of the random nature of sampling, right? Because these 50 students are different from these 50 students are different from these 50 students. So even if we can say that our assumption is the samples from group 1 are equal to the samples from group 2, we would expect for there to be some error. We would expect for there to be some random variability outside of our control, right? Because if we take a random sample of expressive writers, they might be a little above or below their own average. And we take a random sample of non-expressive writers, and they might be a little above or below their own average. So any given random 2 samples will have a difference score that is around 0, but not exactly 0. Sometimes the expressive writers will be higher on health just because of random sampling. Sometimes the non-expressive writers will be higher on health just because of random sampling. So, what our denominator actually does in a t-test is quantify how much we should expect a random sample of group 1 to randomly differ from a random sample of group 2 because we are convinced by an extreme unlikely result. And if we know how much we should expect group 1 to differ from group 2 just because of randomness, then we can evaluate, do our groups differ more than that expected randomness? So our denominator represents the amount of random variability we would expect between samples of expressive writers and samples of non-expressive writers, given the null hypothesis, given that they do in fact not differ at the population level. That's what our t-test does. The numerator says how much difference did we observe. The denominator says how much difference would we expect randomly. Because to claim that the groups do differ, then their difference needs to be above and beyond the difference that we expect to occur because of random fluctuations. And that's why t-test is a ratio, a fraction. It's a ratio of observed difference compared to expected random difference. And if our observed difference is greater than our expected random difference, then we're more likely to conclude that the groups do differ. Okay, I know that's a lot. I know that's difficult to understand. Feel free to watch this again as many times as you need. Feel free to reach out and send an email to your instructor or your TA if you need some help with that. But look out for, I'm also going to post a walkthrough with a math walkthrough of these two practice problems that are at the end of this lecture. So we have two practice problems. I want you to try to do these on your own. This is not for a grade. This is not a homework. This is just practice. I want you to try to do each of these on your own. I want you to use the lecture that I just went through, and I want you to use the PowerPoint slides that'll be posted on iCollege to help you step by step by step conduct these t-tests and reach an APA-style conclusion. And then I want you to compare that to the video that will be uploaded that provides the step-by-step answers to each of these questions, right? Rewatch this video, challenge yourself, see if you can do these practice problems, and then watch the practice answer video that will be uploaded to see how you did. There will also be a homework associated with this, which will mimic these practice problems. It'll be very similar to these practice problems. So make sure you know what you're doing, give it your best shot, rewatch the video, relook at the PowerPoints, and let us know if you have any questions. Thanks, everybody, and I will talk to you next time.